Alright, so before we move on, let's have a look at some of the definitions and basic concepts, okay, regarding phase diagram. Okay, so in order to look at these basic concepts, okay, let me just draw for you. So let's say we have roughly, okay, one type of binary phase diagram here. All right, and so the y-axis is for the temperature, okay, and this is for the composition, okay, in weight percentage, right? So let's say it's a binary phase diagram, so we have element E there and B here. Okay, so now the phase diagram, the binary phase diagram, okay, so we have the first is the solvent. All right, so solvent represent elements or compound that is present in the greater amount or the host atoms. All right, so let's say, okay, we have a beaker here, okay, which is filled up with water. All right, so in this case, okay, we can say that the water is the solvent, all right, because it's the host. Okay, and then if we have solvent, then we have the solutes, okay, to make up the two component system. Okay, so in this case, let's say the solute is sugar that we add in. Okay, we add in sugar into the water. All right, so sugar will be the solvent, the solute, okay, the one that we add, right, in smaller quantity. Okay, now component, okay, is the pure metals, okay, and or compound of which an alloy is composed. All right, so this is, if we are looking at the water and sugar, okay, so it's a two component system. Okay, one is the water and the other one is the sugar. All right, so if we compare that to a phase diagram, okay, of a binary systems, okay, so we have component A here, okay, and we have another component B at this end. All right, so it's a two component system. Okay, so this is a binary phase diagram. All right, now let's have a look at the idea of a solid solution. Okay, so now let's say we add sugar into the water. All right, so next, okay, if we stir, okay, the sugar, okay, inside the water, all right, so eventually it will dissolve. All right, so once it dissolves, okay, we can no longer separate the sugar and the water. All right, so let's say now, okay, so we can no longer separate, so it becomes a syrup liquid. All right, means, okay, sugar has completely dissolved into water and become the solution. Okay, so the same thing goes, okay, for solid. All right, so for solid, okay, we have the atoms, let's say. All right, and then, okay, which is this atom is now the solvent or the host. Okay, and we're going to add a few of the solute atoms. Okay, so let's say it's an interstitial solute atom. All right, so it will sit, okay, somewhere within the interstitial sites of the host. All right, so whenever, okay, these solute atoms, okay, is actually mixing well with the solvent atoms. Okay, so this is what we call as the solid solution. Okay, it's a solution but in solid condition. All right. So now let's have a look at the basic concepts for phases. Okay, so now, okay, when we have water here, okay, in the top figure here, okay, we have water, okay, and then we add sugar. All right, so before the sugar actually dissolve into water, it's a two-phase system. All right, why? Okay, because, okay, we have, okay, the water, okay, in one phase. All right, and we have sugar as the second phase. Right, so a phase is actually a homogeneous portion of a system that has uniform physical and chemical characteristics. Okay, so if more than one phase is present in a system, okay, it is not necessary that there be a difference in both physical and chemical properties. Okay, a difference in one is sufficient. Okay, so let's say for the first situation here, okay, number one here, okay, we have a two component system, right, and we have a two phase exist, right. So the one, okay, for water and the one for sugar. All right, so let's say what if, okay, we add ice cube, okay, into the system. All right, so now it become a three-phase system. Okay, one for the water, which is in liquid. Okay, number two, okay, for the ice cube. All right, and number three for the sugar. All right, so if we stir the water, all right, and the sugar dissolve, okay, in the water, but leaving the ice cubes here. Okay, so now, okay, it's a two-phase system. Okay, one is for the syrup solution, okay, and the other one is for the ice cube. All right, so within this two-phase system, let's say, okay, for the one that we have the syrup solution and the ice cube, okay, there are certain boundaries, okay, that actually separate, okay, the ice cube and the syrup. Okay, so this is the boundaries, okay, that separates the two phase. All right, so phase boundary can be defined as the boundary which is separating the phase in a system. It will exist across which there will be a discontinuous and abrupt change in physical and or chemical characteristics of the phase. Okay, so this is the phase boundary. Right, so if we are looking at the binary phase diagram here on your left hand side, all right, so we'll have the phase boundary here. Okay, all the lines here is actually referring to the phase boundaries. Okay, so it separates the phases, okay, within the binary phase diagram. All right, so in the binary phase diagram, okay, top here, okay, will be the phase for liquid, right, and this is liquid plus solid. Okay, this is also for liquid plus solid. Okay, and this is for solid, this is for solid, and this is for solid. All right, so since, okay, this is a combination of A and B, all right, so this is for solid 1, this is for solid 2, this is for solid 1, this is for solid 2, and this is for solid 1 plus solid 2. Okay, but normally, okay, we'll put it as liquid plus alpha here. Okay, and this as liquid plus beta. So this is the range for beta alpha, this is the area for beta, and this is the area for alpha plus beta. All right, so the yellow lines, okay, are the phase boundaries, okay, that separated all the phases, okay, within the binary phase diagram. All right, okay. what else that we didn't cover here? Okay, so I guess that's fine. All right, now the next one is the microstructure. Okay, so the microstructure is the structural features of an alloy, right? For example, the grain and the phase structure that are subject to observation under a microscope. Okay, so it can be either optical or scanning electron microscope. So in metal alloy, microstructure is characterized by the number of the phase present, their proportions, and the manner in which they are distributed and arranged. Okay, and microstructure of an alloy depends on such variables, okay, as the alloying element presence, okay, their concentration and heat treatment of the alloy. All right, so this is the and this is how, okay, the construction of the equilibrium phase diagram, okay, from liquid solid cooling curves takes place. All right, so this figure 8.3 here, it shows a typical cooling curve, okay, for a pure metal. All right, so at this point, okay, is the pouring temperature, okay, so which is the melting is at liquid state. All right, and it will lead to solidified over time. All right, so the temperature will be declining, okay, until it get to a point here, point B, okay, where it will be in a liquid plus solid transition phase. All right, so at this point, okay, the temperature will remain constant, okay, until, okay, all the liquid has solidified into solid. Then it, okay, the temperature will decrease again as the solid, okay, cool down to room temperature. All right, so if we have this kind of curve, okay, done for many composition, okay, between solvent and solid atoms, okay, which the alloys, okay, so we will have, okay, a few of the cooling curves that looks, okay, like in figure 8.6a here. All right, so by joining all the points, okay, between the transition, okay, for all of this combination of alloys, okay, we will have, okay, what we call as the complete equilibrium phase diagram. Okay, all right, now criteria for solid solubility. Okay, so I already told you just now, okay, what is meant by solid solution. Okay, so but then, okay, even though we can actually add, okay, the solute atoms, okay, into the solvent atom, all right, but there's a limit, okay, to which, okay, we can add, okay, and keep the mixture, okay, in homogeneous form. All right, so for a complete solid solution to occurs, okay, it need to satisfy what we call as the Hume rotary rules. Okay, so we already look at the idea of the Hume rotary rules in the previous chapter. Okay, so let's just recap, okay, what are the rules, okay, within the Hume rotary rules. Okay, the first one is about the crystal structure. Okay, so the crystal structure must be the same. Okay, so if one is FCC, then the other one must be FCC2. All right, and the size of the atom of each of the two elements must not differ by more than 50%. That means, okay, it must be similar in size. All right, and the elements should not form compounds with each other. Right, that means, okay, there should be not appreciable difference in the electronegative of the two elements. Okay, that means the value of the electronegativity of the two elements, okay, must not be differ that much. Okay, and the elements should have the same valence. All right, so one classic example of combination, okay, of elements, okay, that have a complete solid solution, okay, that obey all the Hume rotary rules are between nickel and copper. All right. Alright, so now let's have a look at the binary system. Okay, So binary system is between two components or two compound. All right. So can be divided into 5 categories, okay, such as the binary isomorphous system. Okay, so this is a system with complete solid solution. Okay, for those combination, okay, that satisfy the Hume rotary rules only. Right, and the second one is the what we call as the binary eutectic system. And in the binary eutectic system, it can be further divided into 2, okay, which is the binary eutectic with a limited solid solution, and also the binary eutectic with no solid solution, right? And number 3 is the eutectoid, and number 4 is the peritectic system. So let's have a look at the isomorphous binary phase diagram. Okay, so the isomorphous binary phase diagram is meant only for the combination of element or components, okay, or compounds, okay, that is completely soluble in each other. I mean, it obey 100% to the Hume rotary rules. Okay, so the classic example for the isomorphous binary phase diagram is the copper nickel system. All right. So the phase diagram of copper nickel, okay, looks like this, okay, in the figure on your right hand side, right? So it's binary because it's made of 2 components, okay, we have copper and we have nickel. And then it's isomorphous because it's completely soluble in each other. All right, so there's no solubility limit. Okay, so if we look at the diagram here, okay, so let me just like draw for you one more time. Okay, so this is basically, okay, roughly how the phase diagram looks like. All right, so on this side, okay, this is the temperature and this is the composition in weight percentage. Right, so at this end, right, we have the copper, okay, and at this end we have the nickel. All right, means, okay, at this point, okay, it is 100% copper, and at this point it's actually 100% nickel. Okay, so if we go, okay, further up, okay, and as the temperature increase, okay, at the point of 100% copper, okay, so find this point, okay, where the 2 lines actually met, right? So this is the melting point for copper. Okay, so that is the melting point for pure copper, and the same thing goes, okay, along this line. All right, so we'll come to the point, okay, where the 2 lines met. All right, and this is the melting point for nickel. Okay, that means it's the melting point for pure nickel. All right, and within this isomorphous binary phase diagram, okay, the phases that that comes, okay, on the phase diagram, okay, the top one is the liquid. I mean, it occurs at higher temperature where everything is now melted. Okay, so it's in liquid state, right? And the middle section is, okay, is for liquid plus alpha. All right, so it means, okay, it's the transition, okay, before during the solidification process. Okay, so here, if you look at the alpha here, so the alpha, okay, is the mixture, okay, of the combination between copper and nickel, okay, at certain composition. Alright, so it depends, okay, on what is the composition. Alright, and as it goes down, alright, the last phase, okay, is for alpha phase. Okay, and we have what we call as the phase boundary just now, okay, that separate all the phases. Okay, so in this case, okay, the phase boundary, okay, that separate liquid and the liquid plus alpha region is what we call as the liquidus line. Okay, so this is the liquidus line. So if you look at the liquidus line, above which, okay, everything is in liquid form, all right, and below which, okay, so there are some liquid and some solid. Okay, that means, okay, it already start to solidify. All right, and then, okay, we have another phase boundary. Okay, and this boundary, phase boundary, okay, is the one that separates the transition area with the all solid area, okay, or the phase. Right, so this yellow colored line, okay, is what we call as the solidus line. Okay, solidus line, above which, okay, so there are still some liquid exists, okay, and below which, okay, everything already solidified into solid. All right, so that's basically how we actually look at the phase diagram. Okay, now we look at how to understand and using the phase diagram. Right, so let's say, okay, we indicate phases as a function of temperature, composition, and the pressure. All right, so that's already mentioned it to you just now. All right, so I think already I mentioned all of this. Okay, let's just move on. Okay, so this is something that I already explained as well. All right. Okay, now, okay, let's go straight away to the interpretation of phase diagram. Okay, so during the earlier slides, okay, I already mentioned to you the 4 important information that we can actually gather from a phase diagram. Okay, so we can actually, okay, let's just go back to the slides. Okay, if there are phase presence, okay, composition, fraction, okay, and the microstructure. All right, so now, okay, let's have a look, okay, at this one. Okay, the interpretation of phase diagram. Okay, so that is what, okay, the interpretation of phase diagrams, okay, will looks like. Okay, we are looking for all these 4 information. All right, so the first one is the phases, okay, that are present. Okay, and then the composition of each phase, okay, and also the weight fraction or the amounts of each phase, okay, and the resulting microstructure. All right, so in order to do this, okay, so this is a copper-nickel phase diagram. Okay, for example, okay, the isomorphous system. All right, so let's say we have a composition of an alloy, okay, that consists of let's say 35 weight percentage of B, all right, and 65, okay, weight percentage of A. All right, so let's say this is the alloy composition. Okay, so the alloy composition is normally denoted as C0. Okay, so if you look at here, okay, so this is our C0, which is the alloy composition. So once, okay, you know the alloy composition, okay, what you have to do, okay, is you have to draw a line, okay, a vertical line, okay, from the alloy composition. All right, so this vertical line will actually cross all the boundaries, okay, within the phase diagram. All right, so now, okay, in order to determine all the information, okay, so we already have the composition. Okay, next thing that we need is the temperature. All right, so let's say the temperature is given at T. Okay, so once we know the temperature, okay, you have to draw a horizontal line, okay, at that particular temperature that cross all the boundaries on the phase diagram. Okay, so let's do that. Okay, so this is the line. All right, so now okay, can start, okay, we can start taking the all the information, okay, that we need. All right, from all the lines that we already drawn. Okay, so the first one is the phase present. Okay, so the phase present, okay, is looking at the intersections, okay, of the two lines, okay, the vertical and the horizontal lines. Okay, so let's use different color for this, right? So this is the intersection point. All right, and this intersection point, okay, actually lies, okay, in phase liquid plus solid. All right, so the phases present here, okay, is liquid plus solid. All right, and then we have to determine the composition of each phase, okay, and the amount and fractions of this phase. Okay, so let's go to the second one first. All right, so in order to determine the composition of each phase, okay, so you have to look at the intersections of the horizontal line with the phase boundaries. Okay, so this is the intersection point, okay, of the horizontal line with the phase boundaries. Okay, so we have one composition here and the other composition here. All right, so now, okay, how do we know? Okay, we have liquid and solid. Okay, from the first one we know that the phases present are liquid and solid, but we don't know just yet, okay, which point okay actually represent liquid and which point which actually represent solid. All right, so let's have a look at the first point, okay, on your left hand side. If you look at this point, okay, above this point, okay, is the liquid region. Okay, so therefore, okay, the composition here, okay, is actually the composition for liquid, Cl. All right, and if you look at the second point on your right hand side, okay, below which, okay, everything is actually solid. All right, so this is the composition for solid, or we can call it composition of alpha, right, that represents solid. Okay, now, okay, we have come to know to the second part. Okay, so this is C alpha and Cl. All right, so in order to get to the third one, okay, what we have to do is, okay, we have to draw what we call as a tie line. Okay, right, so in order to draw the tie line, let me just quickly draw another one for you. This is a horrible drawing, but you'll get the point, right? Okay, so let's just do it again. This is A and this is B. Okay, this is in the weight percentage of B. Okay, we have liquid here. We have liquid plus solid. Let's just put the solid as alpha, and this is all solid alpha. All right, and then we have the alloy composition. Okay, so this is a alloy composition C naught. Okay, so let's say, okay, I randomly choose the C naught to be at 35 weight percent B. All right, so this is the line of the alloy composition. Okay, so this is the line for the alloy composition. All right, and then, okay, we need the temperature. Okay, so let's say the temperature is here. Okay, the temperature is here, so we need to draw a line, okay, horizontal line. Okay, and this line of temperature will actually intercepts, okay, with your composition vertical line. All right, so here the point of intersection, okay, is the phase present. So it's within the liquid plus alpha region. So liquid plus alpha. All right, so number 2 is the composition of each phase. Okay, we know the phase is liquid plus alpha, but what is the composition of liquid and what is the composition of alpha? All right, so in order to do this, okay, what we have to do, okay, is look at the intersection point, okay, of the temperature line with the phase boundary. Okay, so drag it down. All right, so we know one of this line must be composition of liquid and the other one for alpha. All right, so in order to be sure, okay, which one is which, okay, so you look here above. Okay, so above which, okay, it's liquid. Okay, so this is the Cl, the composition of liquid, and this one, okay, below which is all solid. Okay, so this is the composition for solid. All right, so it's better if you can actually brought down the whole lines here. Okay, so this is your C naught, this is your C liquid, and this is your C alpha. All right, so we know that C naught is at the 35 weight percent B. Okay, so let's say this is 10. Okay, so let's say this is 10 weight percent B. Okay, and let's just randomly says that this is 70. All right, so this will be 70 weight percent B. All right, so this is the composition of each phase. Okay, so the third one is to calculate the weight fraction. Okay, the weight fraction. Of course, okay, you can always refer to the rules, okay, in which you can do the calculation here, okay, the level rules, okay, but let's just do it the easy way. Okay, so in order to calculate the weight fraction, okay, you have to use what we call as the level rule. Okay, so the level rule, okay, is basically what we have here. Okay, so we're going to use, okay, all of the information on this line, okay, for Cl, C naught, and C alpha to calculate the weight fraction, okay, using the level rules. Okay, so first, okay, let's say we are going to calculate the weight fraction for our liquid. Okay, WL. All right, so liquid is at this side. All right, so liquid is at this side. All right, so if you want to calculate the weight fraction of liquid, okay, so you have to get the length on the other side, on the opposite side of the line. All right, so which is this much. All right, so that is C alpha minus C naught, okay, over the total length of the line. All right, so which is C alpha minus C L. All right, and vice versa for W alpha. Okay, so because we are looking for alpha, so it's on this side, so we have to get the length of the opposite side. All right, so the length of the opposite side is C naught minus C alpha over the whole length of the line, okay, which is C alpha minus C liquid. Okay, so you'll get to the weight fractions. Okay, so or else, okay, you can always refer to the notes here, okay, in order to calculate the weight fraction. All right, so this is given to you, okay, the same thing, okay, that already mentioned to you just now. All right, but if you remember to take, okay, the length of the opposite direction of what we are trying to calculate, okay, so you don't have to worry about the calculation. Okay, so you'll straight away know what to do. Okay, and this is the microstructural development. Okay, so the resultant microstructure, the fourth information that we need from the phase diagram. Okay, so if we look here, let me change the color. All right, on top here is when it's all liquid. Okay, so it's just all liquid. Okay, nothing happened yet. All right, so once it's actually crossing the liquidus boundary, so this is the liquidus. All right, so the solidification will start. All right, so we'll start with a small dots of blue there representing alpha, and as the temperature decrease, okay, within the sorry, within the liquid plus alpha region, okay, so the blue dots is actually getting bigger. It means, okay, more and more solid starts to solidify, all right, until it cross the boundaries, okay, which is the solidus line, all right, so below which everything will be in solid. So all the blue dots, okay, will actually combine with each other, okay, and form the final resultant microstructure. Okay, so all of this is actually the grain for alpha. All right, so it's very easy for the isomorphous system. Okay, all right, so I think I'll stop here. Okay, I'll start again with the next part, okay, where we are going to look at the binary eutectic system. All right.